Welcome to the distinguished lecture series in electrical engineering. It's my pleasure to introduce the first speaker of the series, Ted Rappaport. He is the David Lee Ernst Weber Professor of Electrical Engineering at the Polytechnic Institute of New York University. He's the founding director of NYU Wireless. It's a first academic center combining engineering, computer science, and medicine. It's a really exciting initiative that he's leading. Previously, he founded two academic centers in his previous academic worlds. He founded the Virginia Tech, a highly known center in Virginia Tech, and another one recently in Texas and Austin. He's a pioneer in radio wave communications for cellular and personal communications, wireless communication system design, and lately in broadband wireless communication systems. He has over 100 patents issued or pending in these technologies, and he has co-authored or co-edited 18 books. One of the first textbooks in wireless communications is one of Ted Rappaport's. He's the author of that classic textbook. He's an entrepreneur. He founded TSR Technologies and Wireless Valley Communications. The latter was sold to Motorola. He received a bachelor's, master's, and PhD degrees from Purdue University and studied under two very well-known and distinguished professors, McGillen and Cooper. So it's with this, please join me in welcoming Ted to the University of Delaware.
Thank you very much, Professor Arce. It's a pleasure to be here at UD. And I understand several of you are getting points towards your final grade, so thank you for coming. And I hope that's worth the extra inducement. It's my pleasure to talk about something that I'm very excited about. I think it's going to affect all of our lives. And I think this is where many of us in the room will either be using or doing research on this topic in the coming several years. I call this talk The Renaissance of Wireless Communications, the Future Edge of the Internet. Because I believe while wireless is 30 years old from the early days of cellular, it's about to hit the Renaissance where it pervades everything in our life, becomes seamless, becomes part of the fabric like pen and pencil are. And I hope that this talk can motivate some ideas, some encouraging trends, and also some research that has not yet been published, which I think points to this renaissance that I'm pleased to share with you today. There's this older gentleman and a young teenager at the baseball game, and this old guy's watching the ball game, and the young kid's there on the smartphone, texting away, and the kid looks up to this older gentleman and says, "I really can't relate to you at all. You're older than me. You didn't grow up with the internet. You probably don't know how to text. And, you probably don't even know how to use a computer." And so the old man is kind of watching the game, and he turns over and he says, "Well, Sonny, before you were born, I was working, doing a job, and building all the infrastructure so you can enjoy that smartphone. What are you going to do for me?" So this whole world of internet, it's really a new world. And I teach communications, and I asked the students, my last class at UT Austin, had about 40 graduate students. I asked them, how many of you have listened to an AM radio? And none of them had listened to an AM radio. I couldn't believe it. I've been asking this question for the last several years. And it's gotten smaller and smaller. But now, here were brand new graduate students, and none of them had listened to AM radio. I asked, how many have listened to an FM radio in a car? And maybe 10 students raised their hand. So it's such a different world now with the internet and with access over the web, in the electronic appliance itself. But as new as this world is to the younger generation, to you students, there's a new world coming that's going to come even faster, that's going to displace the way you download your content and the way you get your data. And if we get these slides working, I'm going to give you a glimpse of that world. One thing I always try to stress when I'm teaching is you can have a great idea, you can work the theory, you can do the analysis, you can do the simulations, you can get the right answer many different ways, but if you can't make it work in practice, it's not really worth much. So, it's now that I'm in New York, they say, how do you get to Carnegie Hall? Practice, practice, practice. It's really a good adage. So I'll go ahead with the talk, and I'm sure we'll get this working, but this idea of the future edge of the internet coming in new ways we never thought of, we're just around the corner. Here's why. If you look at all the radio spectrum used today, AM radio, FM radio, satellite, cable TV, cellular, PCS, Wi-Fi, and you take all the spectrum usage, cellular at 900 and 1800, Wi-Fi at 2.4 gig, and you look at the collective bandwidth of all of that spectrum, everything we've ever used in the history of the world since Marconi developed wireless, that entire bandwidth now fits. It all fits within the 60 gigahertz unlicensed band. So all the spectrum that's ever existed now easily fits within an unlicensed band that's been made available around the world, where the FCC and the European governments, China, Japan, Korea, have all agreed on a 4 to 6 gigahertz spectrum chunk in the 58 to 65 gigahertz band. So everything we've ever known on the history of the planet, the spectrum fits within this narrow band. But this is the tip of the iceberg. As engineers are developing the circuits and techniques, thank you very much, developing the circuits and techniques for these, and here's a look at the spectrum band where you can see the 60 gigahertz spectrum on the bottom row. If you read from left to right, each row is a decade of frequency. So you can see cellular in orange is in the 300 megahertz to 3 gigahertz band. And then below it is 3 gigahertz to 30. And all that blue is all the spectrum in the world going up to Wi-Fi and even microwave line of sight. And that all fits within the 60 gigahertz band. But the amazing thing is that CMOS, the chips we enjoy in consumer electronics, the research has taken CMOS up to frequencies much higher than 60 gigahertz. Today, we can make very cheaply, inexpensively, CMOS circuits up to 100 gigahertz carrier frequency, 200 gigahertz, up to several hundred gigahertz. It's an advantage of Moore's law. And already today in products like high-end vehicles, there's 77 gigahertz radar chips being made by the millions. So we're making consumer devices up at this millimeter wave frequency at 60 gigahertz. The wavelength is 5 millimeters, smaller than your pinky fingernail. And on a high dielectric material, it becomes much smaller. So the circuits are there. Silicon is there. In fact, I saw some great work by Professor Dennis Prather working on some amazing stuff up to 300, 400 gigahertz today here at UD. And the tip of the iceberg is here because this is a chart of the atmospheric absorption with frequency and decibels per kilometer loss. And you can see the reason why the 60 gigahertz band was allocated is the FCC and other governments knew that at 20 dB per kilometer loss, you couldn't do much damage. 20 dB, factor of 100. You go a kilometer, it's 100 times weaker on top of the propagation loss. But there are other spectrum bands like 90 gigahertz and 220 gigahertz that actually have less than a dB of loss over a kilometer. And today's base station separations in cities like Beijing and Manhattan are 200 meters or less. So the loss due to the atmospherics, the O2, the oxygen molecules, negligible. What this means is that these future frequency bands are going to be used for cellular, outdoor, as well as indoor, the early Y-gig 60 gigahertz application. And think about this. We've operated the entire world, our entire lifetimes in wireless, in that white bubble on the far left. The 0 to 2 gigahertz range, that's where cellular is today. But if we can get up to these frequencies of 60, 200, and even up at 380 gigahertz, where you can use whisper radios, where radio waves attenuate so quickly you could have short distance whisper communications, with bandwidths, 5% bandwidths on the order of tens of gigahertz, not 50 megahertz or 10 megahertz like we have today. In the last 30 years, while we've been operating in that white bubble, the microprocessor clock speeds have increased 3 to 4 orders of magnitude, from megahertz to gigahertz. The memory sizes have gone up from kilobytes and megabytes to terabytes, 5 and 6 order of magnitude. Yet in the last 30 years, the carrier frequency of wireless has only gone up 1 decade, 500 megahertz to 5 gigahertz. So the dawn of this new millimeter wave, the entire spectrum to the right is before us. And this is how we're going to have the pipes wide enough to bring bandwidth to the edge of the internet, not just indoor, but outdoor, mobile, to your cellular device. So that the teenager of 30 years from now will be looking at you, students, at the baseball game, and wondering how they can relate to you with every bit of data that you ever consumed in your lifetime being delivered wirelessly in minutes or maybe seconds. So we're talking about orders of magnitude increase in bandwidth. This is the spectrum allocation that's going to allow the very early days. Just like, Professor Samini knows this, he was there, just like the very early days of Wi-Fi in 1985 and 1990, when there were a bunch of companies trying to make wireless data work at 900 megahertz. It wasn't until there was a global spectrum allocation at 2.4 gigahertz that 802.11b, Wi-Fi became the global standard, and now it's in every laptop. So we are in the very early days, 60 gigahertz being that first entree into this new world where the renaissance will occur. This is an actual chip. We've built antennas, and when you think about the wavelength at 60 gigahertz, 5 millimeters, it's so small that you can start changing the form factor of cell phones and antennas. You can start thinking about, instead of having to make a laptop, which has 12 or 13 tiny wires that go through the hinge, you can now think about putting wireless antennas on silicon chips all around the skin. These are tiny, these are small, and you can start forming beam arrays. You can start forming antenna arrays and free up a degree of freedom in making the physical mechanical structure. There's no reason why this can't happen. If you look at CMOS, the frequencies, and this is an old chart, are now approaching 1 terahertz F/T amplification, meaning that getting up to the 100, 300, 400 gigahertz carrier frequencies are viable. And as you get up to higher frequencies, the percentage bandwidth being a constant gives you much, much more bandwidth. If you could give a cellular carrier 10 gigahertz of spectrum at a carrier of 100 gigahertz, 10% bandwidth, what would that do? Today, the Verizons and the AT&Ts and the China Mobiles of the world have to deal with spectrum allocations that are 25, 50 megahertz wide. If we could offer them 20 times that, you could immediately start using the same spectrum for backhaul as well as for cellular service. Not only that, these real carriers have a problem managing all the different bands. Many of your cell phones have 4 or 5 band radios in it. 700 megahertz, 900 megahertz, 1800 megahertz, 2.1 gigahertz. All the different cellular bands, and some of you have different bands. Those are 4 different frequency planning where they have 4 different footprints for the base stations. 4 different management issues for spectrum. 4 networks running under one label. You get up to these millimeter wave frequencies, 700 megahertz to 2.1 gigahertz, that's a factor of 3. There's spectrum at 28 gigahertz and 38 gigahertz today sitting there that's available, dormant, from the failed LMDS auctions in the 1990s, where 2 gigahertz of spectrum could be offered to carriers. And you start doing cellular planning at 28 and 38 gigahertz, there's not that much difference. It's not even a factor of 2 difference. So you could do very much the same frequency planning and take out the difference with adaptive antennas because these wavelengths are small. You start getting up to these high frequencies, you can think about vehicle connectivity and loading all the data you'd ever need or want to a car as it goes by a signpost. In fact, you can think about the occupants of the car transmitting huge amounts of data, entire data disks, all the books you've ever read or all the movies you need in a fraction of a second. And the idea of an information shower, no longer will you need a book bag to go to class. You'll take your electronic device, you'll walk under the access point. Maybe you'll be out in the cellular network, and everything you've ever read or ever will need, every book you've ever wanted to read and never will read, can be downloaded in seconds from the cloud as you walk to class, the information shower. And having this massively broadband pipe of data will change the form factor of appliances that we use today, like laptops. Why does there have to be a magnetic drive in my laptop? Or an electronic hard drive that weighs a lot, takes up power? Why can't that be a small RFID-like card in my wallet, on my persons, in my clothing, using a very high data close-range link, perhaps at a whisper radio frequency? You start looking at changing the form factor when you realize that you can very efficiently transmit wireless over high data rates, certainly in close proximity, and as I'll show today for the first time, even in a cellular environment. So changing the form factor and changing the way we use devices today built on legacy concepts, removing the obstacles that give us better power, better weight. There's a lot of control wiring in military, aircraft, ships, tanks, our vehicles. When you have such wide bandwidth, you can actually replace the harnessing that carries control signals and transmit wirelessly around a car, within a car engine, even within a circuit board itself, taking advantage of the very wide spectrum to get frequency diversity that gives virtually perfect reception. And you do it in silicon, removing the mechanical cabling, removing the harnesses, removing the weight and cost, because in commodity, silicon is the cheapest you can do compared to wiring. In fact, one of the executives of the leading electronic companies that are in every major city, CTO of a big company, came to me. He was threatened about wireless. He was worried about 60 gigahertz. What's going to happen? Turns out that the greatest profit margin in any consumer electronics store is on the cables that you buy. They will squeeze the margins and sell at cost the television to sell you the HDMI cable because they make the biggest margin on that. Copper wire is the greatest margin cost and oftentimes the greatest profit in an electronic sale. So if we can remove that, we will reduce the cost of vehicles and appliances, free up flexibility, and bring wireless into kind of this pervasive mode where we're able to exploit it and use it and totally change the form factor. In fact, we looked at a data center. There was a great article by Randy Katz a couple years ago in IEEE Spectrum. Big data Titan boom, something like that. Tech Titan boom. It was a very inspiring article, and it got us to think 30% of the power consumed by a large data center that Google or Yahoo or Microsoft build is wasted in heat. Another 20% is in cooling because of the heat. So basically 50% is lost trying to keep things cool and trying to keep things from breaking. And a lot of that's in the switch. And a huge part of the cost of data centers are the copper or the optical cables that connect the 500 computers together. So we did a link budget to see if you could build wireless, a very inexpensive, simple, off-the-shelf in today's technology, not even considering improvements. And the same 1 watt that it costs to drive a data center cable from one computer to another, that's including all interconnects, drivers, buffers, You can do it in wireless, and the big loss in wireless is the channel, the power dissipated in the channel. It's basically propagation loss. It's not oxygen loss, it's just going the distance. Right? In wireless, you lose your big part of the power early, the first few meters. Then after that, it goes off very slowly. That's why it was great for cellular. But if you can get that power lost back with very directional antennas, because now you have a very small footprint, it turns out you can get great signal-to-noise ratio and data rates of several gigabits per second. And already, vendors are starting to provide these devices. Silicon Image, which bought Cybeam, is making HDMI replacements, several gigabits per second. And some of the standards I'll talk about in a minute are actually commercializing this. But these are early days, because that same technology that comes to Wi-Fi and the close network is going to come out to the cellular world. As engineers, as circuit designers, as network architectures become accustomed to these very high data pipes. So let's look at the antennas, because that's where we can get a lot of gain back. That's where in the channel we can save some of that power. If we had very directional antennas, steerable, with very small physical footprint, with very large electrical gain because of the small wavelength, we can actually do better than today's copper or optical cable that each draw about a watt. In fact, we could totally remove the constraint of putting equipment in racks where heat can collect, where switches can get hot. And we can start distributing this data center using wireless beams and interference mitigation, interference cancellation within a data center. So not only will we save on power, but we'll also reduce heat, thermal buildup, by distributing the actual switching mechanisms. So here's an example of a 2-element Yagi built on 1 millimeter by 1 millimeter silicon. They're very small, and on-chip antennas or on-package antennas remove the interconnect problem. You know, right now to connect a 60 gigahertz signal requires an expensive, lossy cable, subject to breaking. If we can integrate all the electronics, we remove that loss, we make it mechanically sturdy, and we make it manufacturable. So being able to put antennas anywhere we want, placing them almost like freckles on your face, putting them anywhere on the device that fits, and then letting beamforming and phasing make the antenna work is a new approach. Now the trick in doing this in CMOS is that you've got bulk silicon and you build the whole connection lost. You build the whole circuit of this 10 micron multi-layer aluminum or copper at the very top or gold, 6 metal sheets, and it's basically like a multi-layer circuit board. And the semiconductors, the magic happens between the bulk silicon and the metal layer. But people are trying to do this, and here are some of the early results of on-chip antennas, directional antennas that can be built in silicon. This is about 1 millimeter long. It's a 60 gigahertz 3-element Yagi antenna. Notice the efficiency is only 2%. You lose 12 dB, a loss of 12 dB. The energy is wanting to go into the substrate and not out into the air. So here you have directionality but loss. What good's an antenna that's lossy? Turns out a lot of cell phone antennas are lossy, especially when you put it on a metal counter. Right? There's a company called Paratech that Research in Motion just purchased, which does this automatic Viswar tuning. It can actually tune the antenna. If you put the antenna where it tunes it, that kind of technology will probably become popular in phones in the future. But here we have the basic silicon with an epsilon R of 4 trying to pull the wave into the bulb and not letting it radiate. Here's an inverted F antenna, again 2 millimeters wide, operating at 60 gigahertz, negative 19 dBi gain. We decided to do something very simple to see if you could actually get an antenna that doesn't lose you anything but gets you directivity. So we went back to the literature and looked at the rhombic antenna that was originally used for shortwave radio broadcast and shipped to shore back in the 1930s and 1940s. And you needed giant antenna farms, 50, 60 acres, and you put these antennas up over the ground. And that's how you talked around the world before there were satellites, before there was the internet. And we thought, well, let's take it up to 60 gigahertz, where instead of needing all this land, we could build it on a 5 millimeter by 5 millimeter tiny chip. And so this is, we believe, the first on-chip rhombic. And the beauty of a rhombic is it's multiple band. It resonates at harmonic. So this was actually a 30 and 60 gigahertz rhombic antenna, and you can see we actually got a gain of 0.2 dBi, basically no loss, but with a good directional pattern and 85% efficiency. So you can, with some very crude approaches, and there are other ideas that you can do that really improve this, you can actually get steerability, directionality on silicon, very small, that will actually radiate in a particular direction. And then you can phase these and create any antenna pattern you want, electrically steering, electrically phasing. So that was pretty exciting. And then we thought, well, if we're going to do this for WiGig and Wi-Fi, can it work for cellular? See, the entire cellular world has never believed we can make cellular work at millimeter wave frequencies. They've said rain will create too much loss. The path loss is too great. You know, there are all these myths. So we set out to see empirically and analytically if these myths are true. And I'm here to tell you that I'm very excited that cellular may actually work not just as good, but better at millimeter wave frequencies than today. Imagine that. More bandwidth, orders of magnitude more bandwidth at the higher spectrum, better performance. Here's why. First of all, we took a look at foliage. Early studies in the 80s from 9 gigahertz to 96 gigahertz showed, not surprisingly, that you get more propagation loss going through foliage the higher frequency you go. The upper left graph is the path loss or received signal level at 9.6 gigahertz. And the bottom right graph is the loss at 96 gigahertz. So an order of magnitude of spectrum frequency change. You get much more loss, 30 dB more loss going through foliage at 96 gigahertz, and it's much more variable. The leaves become electrically large at 96 gigahertz compared to 9. That was worrisome. It shows that wind will modify the link. It shows that there's more attenuation, as most people believe, due to foliage. But then we looked at LMDS work, and some of this was done at Belcourt. And LMDS was really quite the rave in the mid-90s, late 90s, when Reed Hunt at the FCC was going to deregulate the last mile and allow competitive local exchange carriers to compete in the last mile. And there was this spectrum at 28 gigahertz auctioned off, pretty inexpensive at the time, because 28 gigahertz was a technological leap in the 1990s. You see, CMOS hadn't caught up yet. So LMDS unfortunately got caught in the dot-com crash, and a lot of great executives who had left AT&T and billions of dollars invested into buying the spectrum and creating these point-to-multi-point links across buildings in the urban centers across the world basically went bankrupt, and that spectrum sits largely unused today. But today, now, in 2012, the CMOS capabilities, the ability to make products at these millimeter wave frequencies of 28 and 38 gigahertz exist, because we're doing it at 60 for 802.11 AD. And here's some work that first got us thinking that maybe, just maybe, millimeter wave cellular could work. This is work showing that if you put a rooftop on top of a house in a suburban area, and you went 1, 2, and 3 kilometers away from a 28 gigahertz LMDS base station, you would be able to make the link 14% or 86% of the time for 1 kilometer. 100 minus 14 is 86. You could make the link 72% of the time for 2 kilometers. And if you look at where cell site sizes are going, femtocells, HetNets, and just the deployment of today's cell, we know cell sizes are going to be much less than a kilometer. So this looked like pretty promising, 14%. Even down at ground level at 3.4 meters, close to ground level, 3.4 meters, that's still 10 feet above the ground, 11 feet above the ground. Half the time you could make a link. And this did not use any vertical elevation tilt. It was just scanning on the horizon, trying to form the best beam possible between a transmitter and receiver with a directional antenna. So that was encouraging. Maybe it could work. And then we looked at rain. People know that rain attenuates the higher the rain rate, shown on the left curve. And in fact, the raindrop size determines the attenuation. And if you look at, say, the 28 and 38 gigahertz range, look between 20 and 50 on the upper graph. A heavy rain is about 8 millimeters per hour, and a super heavy torrential downpour is 25 millimeters to 50 millimeters per hour. At 25 millimeters per hour at 30 gigahertz, if you look on that curve, attenuation is about 6 dB per kilometer. If it's a cell size of 200 meters, you divide by 5. So the rain attenuation is only about 1.2 dB over a 200 meter cell at 28 gigahertz. 1 dB. Now 1 dB is 25%. So that's a lot. But imagine if you have this array of small antennas embedded in your device, on the skin of your smartphone, on the laptop, able to make up 1 or 2 dB in gain electronically. You can make that link up very easily. So that was very encouraging. And even up at 60 gigahertz, look at the raindrop. Drop radius 0.5 at 60 gigahertz on the right-hand curve, 10 dB per kilometer at 60. 200 meter cell, again, you're talking only a couple of dB. This was remarkable because no one had really looked at this before to consider outdoor cellular. It's very viable. So the key is, can you make it work? Can you connect? Is there outage if you randomly put up base stations and moved and used your cell phone the way you want to? No one had studied this. And what's the multipath like? See, the beauty of using spatial antennas is you can form spatial arrays and exploit the time domain multipath to use both space and time for diversity. And actually put a rake receiver in the time domain and also combine paths in the space domain. Imagine forming multiple beams, collecting the energy, basically doing a spatial rake. What CDMA did, but now moving it to the final frontier, space. You see, that's a whole new dimension for wireless. And you can do it now at these very small wavelengths. In fact, years ago, we looked at angle of arrival profiles inside buildings and saw it's very rich. There's rich scattering. At 60 gigahertz, you are reflective. At 60 gigahertz, a lot of things are reflective. And while foliage is an attenuator, if we can get around the foliage, we can bounce off a lamp pole or a building or a vehicle, there's actually a lot of rich multipath that we can exploit to make the link, to collect the power. So, we set out to measure in Manhattan this past summer, 28 gigahertz to see if it could work for cellular. To do this, you have to build your own custom hardware because today you cannot buy off-the-shelf equipment fast enough. Now, we're working with one of our industrial affiliates at NYU Wireless, National Instruments, driving their product development to try to get their speeds up to where we can kind of create the test and measurement equipment and the bench test for these products of the future. But for now, we have to build it ourselves, custom ECL logic and circuit boards and very careful digital design. And then we have up converters and down converters. These base stations are horn antennas connected to RF amplifiers. And we use horn antennas because today we can't build those phased arrays. But we know they'll be built sometime. We'll build them in silicon. So we use horn antennas in order to estimate what the antenna patterns will look like when we finally put them on the skin of devices. And we build a sliding correlator. It's a spread spectrum system pioneered by Don Cox at Bellcore in the 70s, Bell Labs. And we have I believe, the fastest sliding correlator in the world. 800 megachips per second. So 800 megachips is 1.2 nanosecond pulse. Radio waves travel 1 foot per nanosecond. So we're able to resolve multipath to 1 foot, roughly, third of a meter. And so we actually go out into the environment, and I've got a great team of undergraduates. But first we measured at the University of Texas. And the Texas measurements were encouraging. We did both peer-to-peer, because we'll take advantage of peer-to-peer communication in cellular in the future, and saw there are a lot of paths, a lot of multipath to exploit. We'll have to equalize it. And we saw that in the peer-to-peer, energy comes from everywhere. If we're trying to talk to each other in this room, energy will bounce from many different places, and we can make a link. You can see on this graph going in the vertical axis the receiver azimuth angle, where the receiver looks with a directional antenna to make a path, and where the transmitter is pointed. So the transmitter may be looking there, the receiver may be looking there, and it creates a link. We use 10-degree beam with antennas everywhere and just kind of methodically chunk through all possible pointing in azimuth and elevation to try to make links, to see if we could find the energy. And then we went around the campus at University of Texas, with these base station locations on the left and measured to see what would happen if we were in typical places where you'd want to use your cell phone. And when you put the base station up on a building, got the antenna above the ground, just like Bill Lee found in the very early days of cellular in the 1970s. He found that as you get the base station up high, not surprisingly, it's the energy down around the mobile where the scattering happens and where you want to look. The mobile wants to look around a lot. That's the vertical axis, receiver azimuth angle. It's all over. But the transmit angle really is within a plus or minus 30-degree cone. 60-degree sectoring will work on 5G cellular up at 28 gigahertz. We found this time and time and again. So if you look plus or minus 30 on the transmit's azimuth angle, that's where most of the energy is. So you'll have transmit beams that can form maybe at 60 degree. Maybe they can get tighter. Maybe they'll form tight beams. But to find the mobile, you can really stick to 60-degree sectors. And we looked at many different heights above ground and many different locations and found very much similar properties. It's that plus or minus 30-degree width, the 60-degree width for the base station at these frequencies. And then we looked at path loss, and this was probably the most remarkable result. Not surprisingly, at 38 gigahertz, line of sight, when you have a line of sight between the transmitter and receiver, you get near free space. N equal 2, d squared path loss, n equal 2 is free space, and you can see the best fit is n equal 1.89 or n equal 1.9. But this is now looking at if we had an adaptive antenna at both transmitter and receiver and could move them electronically and get them to point to links, what would the resultant path loss be? And this is the most remarkable thing, other than the outage, which I'm going to get to in a minute. The remarkable thing is these are very similar to today's cellular environment. That is, cell phones of today have very similar path loss as a function of distance. The received power falls off very similar at 28 gigahertz than at today's 2 gigahertz. This is a surprise. No one knew this. Now, granted, I'm using higher gain antennas, but what's even better is when I happen to find the best link with the transmitter pointing at a particular direction on the roof and a receiver pointing at the other best direction to find the best link, the strongest link, I reduce the path loss exponent from 3.86 in the top graph with a very narrow 10-degree beam width. I drop it from 3.86 to 3.2. You multiply that by 10, it's 38.6 dB per decade versus 32 dB per decade. I'm able to get back 6.6 dB on a link by picking the best obstructed path when things are in the way. I don't have a clear shot to you, but I point and I manage to find it over all these different measurements, 50, 60 times in Texas at different base stations. I can grab 6.6 dB. You know what 6.6 dB is? That's a lot. 6 dB is a factor of 4. I'm talking about increasing the radius size almost double. Double the radius size if I have the right pointing. And this happened even on the bottom graph with wider beam widths, 30-degree beam widths at the receiver. Notice I go from 3.18 to 2.56. I go from 31.8 dB down to 25.6. Again, a 6 dB savings. Using the best path, if I could find those pointing algorithms, whatever they are, I don't know them yet, I can make the link better than today's cellular. This is better margin than today's cellular phones. Less drop call, less power used. It's remarkable. Now, we'll have to put the power into the phasing, so we'll spend something there, but as we integrate, we can get that down. So this was quite a shock. Didn't expect it. It shows that cellular actually can improve in coverage by exploiting the multipath and the reflectiveness and the diversity of the environment. RMS delay spreads are typically larger than today's cellular at 38 gigahertz because you don't have the oxygen attenuation. And then we went to outage to see if we just randomly picked 50 locations. 53 random locations. Put it in just took the measurement system over. What we found is everything within 200 meters could make a link. We never had an outage within distances of 200 meters. That's today's cell size in those major cities. That was astounding. So millimeter wave frequencies could work, and so we decided to take it to New York City, where Cellular started, where the Bell Lab's early work measured on top of the Empire State Building. And this is using Manhattan as a laboratory, the crucible in which we can study and invent. Now, let me tell you, making measurements in Manhattan is quite an experience. This is Brooklyn. This is the NYU Poly campus. And looking north, you could see the Manhattan Bridge if we went a little further. And so we put base station on Rogers Hall, one of NYU Poly's building, and went around the campus. And then we went to Manhattan, and we put base stations on top of the Kohl's Gymnasium, 2 stories, and on top of the Stern Business School, Kauffman Business School, 5 stories. We had 3 different base station locations. And let me tell you, as a new professor at NYU, I went and met the New York Police Department, the New York Fire Department, the head of public safety, and eventually the provost. And over a course of 3 months, got permission from all the constituencies to actually get access to rooftops at NYU and to make these measurements. I was told I'm the first professor ever to do that. They've never granted rooftop access. We had police coming with us all the time with this big measurement cart. We had police up on the roof at the transmitter. And all summer, I took a team of undergraduates who were the most motivated, high-energy, courageous students, and we went out and made the world's first measurements at 28 gigahertz in Manhattan. Here's Felix Gutierrez, my graduate student, on the top of Rogers Hall with the base station, the horn looking at the building. The new NYU Wireless Center will be in that building right below the clock. So he's up at about 6 stories. And then here's what the measurement cart looked like. It's a big, big apparatus. It's this channel sounder measuring the channel. And if you look to the far right, you can see the antenna horn staring out at you, that kind of copper gold rectangular aperture. And that was on a motor, a very precise drive motor that can move over very small millimeter steps in distance and also very accurate in angle. So we'd spin that all around systematically, looking for energy, emulating what future cell phones will do with adaptive antennas, in both azimuth and elevation, and moving at very small scale over a track to understand how the channel fades. And here we are on top of the Kauffman Stern Business School building, looking out on West 4th Street. And here's the student team doing calibration. It's a lot of hard work, calibrating, making sure the system works every day, taking it out on the street. We met all kinds of people who wondered what we were doing. They wondered if we were looking for ghosts. Really. There was a homeless person who started asking if we were messing with his brain. Were we like taking his thoughts? We saw it all. And there were sometimes when we were happy that the public safety people were with us. NYU is terrific. I mean, they really are excited. And we're having a big luncheon for all the people. There are about 20 people we had to get approval, including risk management. And we're going to give them all a lunch and show them this slideshow and show them how NYU is changing the world in this. Here we are calibrating, and we did this every day. And, it's about $1 million worth of equipment we're rolling around there on the streets. And this is us taking measurements with the base station behind the building. This is the Silver Tower where faculty housing is. This is the famous Picasso. And we found big multipath here off the back of the building and off the Picasso statue. The point is, we also went indoor and outdoor. We did penetration measurements. We got scattering measurements. These undergraduates are writing their second conference paper and their second journal paper. And they just started sophomore year. And they know this is the future of wireless. They're claiming their future. And but taking measurements is scary. This is an example where the students were in the building, and all of a sudden these fire trucks pulled up. And I was outside, and all my students are inside. And they wouldn't let them out. They couldn't get out. The door was like the fire door had shut. And I'm thinking, my students are going to burn up. They're in this building. Luckily, it was a false alarm. But you see all kinds of crazy things on the street when you're making measurements. It's not for the faint of heart. But let me show you some of the data that the world has not seen yet. Okay, this is an example in Brooklyn with a base station up on a 6-story building. Receiver is, it's 132 meters away, about 100 feet away. And this is in a line-of-sight condition. The antennas pointing at each other using 10 degree beam width at each antenna, 25 dB gain in each antenna. We're able to make about 160 dB link margin, which is very comparable to cellular systems today. Very realistic, very fair measurement. And you can see the channel is perfect. It's almost like a perfect delta function. Bing, a perfect spike. No multipath. It doesn't even fade very much. But at the exact same location, if I turn the antenna to where the transmitter is pointing at -5 and down -10, and my receiver's down over at 120 and looking in a different direction, at the exact same location, this is the channel I see. Delay spread out to 100 feet. Lots of rich multipath, which I can collect. So if I can form the multiple beams, I can not only capture energy in space, but I can also use time diversity. So I could actually code this to create a more robust link. Here's an example in New York City where there's diffraction. And this is a typical multipath delay profile. But you can see the path loss is about 69 dB, small RMS delay spread, several components by which we could build a rake receiver. Certainly 3, as we do today at CDMA 2000. So there's diversity, and we can make these links. In fact, not only could we make links using a 10-degree beam width, we can form typically 10 to 20 different discrete paths, different links at any location. Think about that. If we can form multiple beams, we can collect the energy from many places, bring it together, and these are some of the world's first polar plots at these outdoor cellular frequencies at 28 gigahertz. This is over 135 meters. And we're getting a strong signal at 240 degrees and at 0 degrees. And also at 10 degrees. So you might have 3 beamforms and 3 rake receivers to combine space and time and collect the energy. So this is very early days. There's been a lot of interest in this work, but it's really, I think, the start of what I think will be the next revolution in wireless. It's basically using space and taking advantage of CMOS and the movement at 60 gigahertz to move the whole cellular band and bring that huge pipe down to your consumer device, whether it's in the house, in the apartment, in the car, or in your cellular handset. So it's an exciting frontier, and I think this is where we're all in wireless going to be able to work and apply a lot of the efforts we've been working in other areas. Compressed sensing certainly fits in, figuring out the sparsity of multipath, the time delays, where to point the antennas, beamforming algorithms. There's just so many opportunities here for this new field. And the reason why I believe it's going to happen, why this renaissance will happen, where this bandwidth will come to us and be pervasive, is that companies today are building the 60 gigahertz product, and that's going to build the expertise and the technical know-how, the reservoir of experts, bring it into academia, bring it into companies that will take it out into the $500 billion a year cellular telephone world. So, how do we really make this renaissance happen? You know, I think this is one way, but the fact is it's all of you in this room. And it's all of us working at NYU Wireless, and it's really the entire community of wireless engineers that want to look at this new frontier, the spectrum frontier, that goes far beyond anything we've ever done since Marconi started, and where the bandwidths start to go up by orders of magnitudes just the way PCs started to change in the early 1990s. I believe we're at the same point for wireless. And I thought I'd just tell you a little bit about NYU Wireless. It's a research center. I think it's unlike any other because we're bringing together medical doctors, computer scientists, and wireless communications engineers. So we have graphics, data center expertise, algorithm, data mining, big data, combining with surgeons and anesthesiologists and imaging people, the experts in MRI, along with the conventional electrical and computer engineering work that NYU Poly is already well known for. It's a faculty that's really very collaborative. I've seen wonderful collaboration here at UD. I've really enjoyed my visit. Len loaded up the schedule, but I've really gotten a great chance to meet a lot of you and see some exciting things. We have a very vibrant environment at NYU Wireless as well. And you can see some people like David Goodman and Henry Bertoni, 2 heroes of mine, and probably several of you know them in the room. They've kind of come out of retirement to come back. You know, they're finding a place in NYU Wireless and getting energized by the new research problems. We have doctors. Dan Sodikson down on the bottom left, 3N, is designed the first parallel MRI coils that really is just like doing MIMO, but in MRI imaging. And we have a number of surgeons as well. We're off to a quick start. We've got industrial affiliates, a number of sponsors involved in the center. It's a very fast startup. It's a very exciting time. We're able to now start funding fellowships, really for the first time in many years, and we expect a lot of growth. There's already 100 graduate students and 25 faculty involved. We're hoping to grow 20 to 30% over the next couple of years as companies come on board. And just a word about NYU, because people don't think about NYU as an engineering school. It's the largest and oldest private university in the U.S. It's about 51,000 students. It's a global network university. It's very highly ranked, but it's only recently acquired engineering, having lost engineering in the 1970s. It's acquiring it back with NYU Poly. And this idea of bringing wireless computing in medicine is starting to catch on. This is something we were invited to in China, where they're bringing scientists, engineers, and physicians together in their first international conference of cardiology that brings these three together. Did we influence that? I don't know, but I seem to see this theme emerging. And it's a very exciting theme because we're now getting into the operating room. It's very fun hanging out with the doctors and just seeing how they are really engineers of the human body. This is at the NYU operating room, one of the many hundreds of operating rooms, and this is where wireless and medicine need to come together. This is actual footage taken. I won't run a video, but this is what it's like in a real triage center daily at NYU. NYU, by the way, is one of the top university hospitals in the world, top 8 in the country. They spend $250 million a year just on IT. That's a huge IT spend for equipment, wireless, medical records. That's a $2.5 billion a year enterprise. It's bigger than a lot of publicly traded companies. And we have access to this. They want NYU Wireless. They need help. There are a lot of problems with the devices, so obviously cutting the cord is an obvious solution. But in anesthesiology, these are the docs that have to keep you alive while you go under. They're the ones that have the greatest risk. They have to keep the patient alive, and they have all these machines they're connected to. And it's a mess. In the medical world today, these devices are not interconnected. They're not coordinated. There's walled gardens by every manufacturer to keep everyone out. So the doctors are looking at 6 to 8 screens when they're doing a procedure, a surgery. And they, the doctor, is really the router, the server, the signal processor. We can take everything we do in DSP and communications and really improve and reduce the cost of healthcare if we can get in and break that and bring standards from the cellular world into the medical world. Lower healthcare costs. And so we have buy-in from the cardiologists, from the anesthesiologists, from the brain surgeons. And, they want to make sure that they can measure the oxygen content in the brain. 30% of your oxygen is used by the brain. It's kind of like the switch in the data center. 30% of the power is used in the switch. 30% of the power is used in the brain, oxygen. And so there's great monitoring opportunities. Cardiac EP is a specialty at NYU where if you have AFib, your heart's racing, you can actually go in and burn tissue. If you burn the right tissue, it stops the conductivity. Your heart no longer races. Happens as you get older. They don't know why it happens, but as you get older, some people have racing heart, and if you don't take care of it, it can be catastrophic. So NYU is one of the world's leaders, but they want better resolution. So we can bring wireless and imaging into how they're moving around in the heart to burn this tissue. We can use propagation to figure out how to take the cauterizing energy, the RF energy, at 10 megahertz that they actually use to burn the tissue, and do EMAG modeling with our MRI people. The MRI people can get very good specific absorption rate models in 3D of the heart, use that to estimate what heat source will do to burn and get a much cleaner burn. We're talking burns on a fraction of a millimeter. To burn the tissue away that causes the conduction that causes your heart to race. And this is what it looks like. See that big monitor in the upper right? These are what the doctors are looking at as they do the procedure and move these catheters around and start burning the tissue. It's incredible. So cardiac EP is a great opportunity for wireless. And we're actually working on not just the probes and the modeling for imaging, but we're actually now looking at devices that can replace some of the cords and making wireless standards in the hospital. using chips that we can make. Implantable devices are also done at NYU, and wireless is obviously there, near-field communications, charging, figuring out new ways to couple energy, harvest energy. Very exciting opportunity. And then today's state-of-the-art electrodes are very crude, very coarse. This is an example of an electrode on the brain. Very, very coarse. 12 million neurons on one interface. But we've developed circuitry, organic circuits, that can go in and provide much, much greater resolution, much smaller spacing. Now, all these have wires. So you take this and put it in the body, and then you have 40 wires that have to connect to the wall. An epilepsy patient, for example, has to stay there for days with 40 wires, heavy, connected to the wall. Perfect opportunity for wireless. Imagine wireless devices there. So, in conclusion, I've presented what I think is an exciting way forward for the future of wireless. It's the millimeter wave revolution. It's not the wireless revolution. It's going up to that wide spectrum. It's kind of like the explorers. You know, they came to Manhattan, Hudson. They bought the island for $20 or whatever it was. And then they had the land rush out to Texas and Oklahoma, this wide open space. And people settled west. We're about to go west in frequency as we go from 5 gigahertz up to 50 and 500, where this wide open frontier opens up. It's going to be an exciting future, and this will bring in the renaissance when wireless becomes part of everything we do. And we don't connect with wires. We connect wirelessly, and our devices are connected wirelessly. And we now have the capability to do it. So I hope this has motivated some thinking. I hope it motivates some research. But probably for the first time since I was a young professor 25 years ago, I really feel like we're at the dawn of a whole new age, a whole new step function change. I wrote a paper in 1991. It's titled The Wireless Revolution. It's kind of interesting. I gave a keynote a couple weeks ago, and someone asked me, did I ever predict that taking work from the Wi-Fi indoor world would get out to cellular? Had anyone ever proffered that idea? And I said, I think I wrote about it in 1991 in this Wireless Revolution paper. In fact, I went back and read it. And not only did I predict that, all this work trying to get wireless local area networks to work could be used as kind of a peace dividend for the cellular world, but I also predicted that by 2020, over half the world's data would be carried by wireless. Now that was 21 years ago when I wrote that paper. And I think if this comes through by 2020, it may happen. I don't know, we'll see. But I think this is the beginning of the Renaissance, and I appreciate your attention very much. Thank you very much for having me. Well, it's a great question. The question was, at what frequencies will you be able to have this rich multipath environment and which frequencies you won't? You see, we've never been able to exploit multipath like this in today's cellular because today's carrier frequencies of 2 gigahertz have a wavelength that's about the size of 6 inches. So to make a very highly directional antenna would take, 2 feet or 3 feet, and we can't walk around with an antenna that big. So we could do it at 2 gigahertz today if we wanted to walk around with giant panel antennas on our back. We don't want to do that. So it's as you go higher and higher in frequency, as long as there's not a lot of additional path loss due to O2 or water molecules, but we can make the antennas directional, we get this. That's why I call it space the final frontier. We're taking advantage of the small space of the antenna as the wavelength shrinks so that we can build high gain in a small physical footprint, and at the same time taking advantage of the spectrum where I don't have large attenuation loss due to the oxygen or due to rain. So 60 gigahertz, this won't work as well. We've measured it. You can't go 200 meters. You can maybe go 120. That might be good enough for some backhaul. And the reason why 60 gigahertz doesn't work is I've got the 20 dB per kilometer, which is the same as 4 dB per 200 meters. But if I give an antenna that now gives me 4 dB more gain, remember that's not hard to do when these things are so small. I can even overcome that. So it becomes a whole new world of trade-offs that we've never done in wireless, where you actually have to look at the atmosphere having not just propagation path loss, but also molecular path loss and rain path loss. Hail and ice will also be sleet will also be an issue. So we can go back to the satellite world that did this in the 80s and extract all those measurements that NASA did and ESA did, European Space Agency, and start using it for outdoor. Does that answer your question? Yeah, question here.
What kind of bit rate do you envision in the 60? Because I saw the 20 gigabits per second, but I wasn't sure if you're referring to what you envision. What do you think is?
Yeah, I think we're 5 to 10 gigabits per second in a mobile environment. Very doable. Cell phone. Yeah. Yep. Yeah, you think about multi-level modulation, you think about very directional antennas. We'll have to follow the beams as we move. Doppler's not an issue. In fact, Doppler's an issue, but it's easy to engineer out because Doppler's simply related to the frequency and the wavelength, and that defines the packet size. And the whole future of wireless needs to get smaller and smaller latency. That's what LTE brought. It went from latencies of 10 milliseconds down to 1 and 2 milliseconds, which is what you need, small latency packets so you can get the data in and out for the web, right? And so the Doppler will define packet size now on the order of 100 microseconds. So you'll have packet size 100 microseconds, 500 microseconds, but the data rates will be so high, 5 gigabits per second, you'll still get several thousands of bits in a package, and then you'll re-equalize, you'll retune your antenna. That's kind of where we're going. Yeah, great question. Thank you for asking that. I was waiting for someone to ask that. What happens when you go inside? What's the outdoor to indoor penetration? That's a problem. Metallized glass looks like a huge attenuator, 30 to 40 dB in that one picture going through the glass. Other glass is good. We've actually been measuring a lot of that. So I think the future of wireless will be this outdoor network where you pay more for the bits. You get this huge pipe. And there'll have to be some transition, maybe a switch off to Wi-Fi, into 802.11n or 802.11ac. So coming from outdoor to indoor at these very high data rates. And that brings in whole new issues of how you're going to cache data, how you're going to buffer data for video. How are you going to take this world where you have a discontinuity as you walk into the building? How are we going to, is it going to be repeaters, new products that are repeaters at the interface of where humans walk in and out? Is it going to be a make then break? Is it going to be smart cell? It'll obviously be cooperative, right? But that's a problem, more so than today's cellular, because you can get in and out of buildings easier at 2 gigahertz than you can at 28 and 38. We haven't published that. That's anecdotal, but we've seen that and we've been studying it. We hope to have some good data on that in the next few weeks. Yes.
Or whatever.
Yes.
So do you think that it's going to be feasible at some point to, at the same time that you are trying to communicate data, sense the environment by using that electrical signal?
Yeah, well, I think that's kind of what we do now in cellular. We're actually kind of sounding the channel when we have, our overhead. In fact, some of the colleagues at Drexel are working with Len Samini here on reducing overhead. Whenever we do a packet, we're basically kind of sensing the channel or sounding the channel or compensating. So we'll continue to do that. But what's interesting is we haven't tried it at these frequencies. So we're going to find all kinds of new things, whether it's leaves or whether it's raindrops or whether it's...
I was thinking more about using that to have better weather prediction, for example. Everyone, have a device that is sensing how is the weather.
That's interesting. That's interesting. It actually may happen. What's amazing is we have so much bandwidth. We could do that.
Yeah.
We could take advantage of this huge 5, 10, 20 gigahertz band to do all kinds of things we've never thought about today's cell phone doing. Whether it's doing an image or a radar or seeing what's around the corner. We can do a lot of things wirelessly with this broad spectrum. Frequency gives us diversity. Diversity allows us to fill in information. Good point. Yeah, Charlie.
When do you anticipate the electronics catching up and being able to implement rate receivers at these frequencies?
We're there now in a lot of aspects with 802.11ad. The WiGig Consortium, Wireless HD. I got the CTO of Dell, his office, gave me one of the first Dell laptops that had a 60 gigahertz chip in it, and they put my name on it. It was really exciting. And I said, wow, where'd you get the silicon? And it was from Silicon Image, I believe. And this is a year ago almost. It was early, but they were getting multi-gigabit per second data. Now, how do you save the power? How do you integrate the electronics? How do you really make it efficient? We're in the very early days of that. Think the early days of Wi-Fi. Remember your 802.11, plain 11 routers were this big and only went 1 megabits per second, and then a few years later they were 11 megabits per second, then 54 megabits per second. We're kind of starting that now. But I think we're 2 or 3 years away from having a prototype that does several gigabits per second outdoor following beams as they steer. And if the spectrum allocation at the ITU follows, it could be that you could have these 6, 10, 20 gigahertz, 28 gigahertz bands allocated 5 years from now. Maybe less. So you could see handsets 2018, 2019. And if we can get that path loss the way we measure, actually better than today's cellular, and have more diversity to keep the call from dropping, and I didn't mention, these directional beams create a huge win for us in that it makes the interference lobe very narrow. So the likelihood, probabilistically, of interfering becomes smaller because we're sending out very focused energy and not today's cellular where the energy goes everywhere and interferes with you. So if I point at you, I will interfere with you, but if I'm not pointing at you, I won't interfere. So we're going to get improvement. I'm here to tell you, I believe cellular will be better at these millimeter wave frequencies, not just in the data service it provides, but in the coverage and experience it provides. And the world doesn't know that yet. You're one of the first audiences hearing this. But if my students and I do our job, the world's going to start coming around to this.
Well, Ted, thank you very much. It's a pleasure to have you.
All right, thank you. Thank you very much. Appreciate it.